Okay, so let us continue with our discussion. You see, the last lecture we derived certain important properties of the fundamental group of Riemann surface, namely we found that the Riemann surface is the fundamental group is torsion free, namely you cannot have any elements of finite order, okay. And we also found that the only types of elements that you can get in the fundamental group are the Moebius transformations which are either parabolic or hyperbolic, okay. So you cannot have elliptic elements in the fundamental group, you cannot have loxodromic non-hyperbolic elements, and of course in all this we are identifying the fundamental group of the Riemann surface with the choice of some base point with the deck transformation group of the universal covering, and we must remember that the deck transformation group is a subgroup of Moebius transformations, okay. Fine, so I will now have to go on with trying to get the classification of Riemann surfaces which have universal covering the upper half plane and which have abelian fundamental groups, okay. So that is what I am going to start with. So let me write that down. Riemann surfaces X with pi 1 capital X comma small x abelian and universal covering space U which is a set of all Z and C such a real part imaginary part of Z is positive, okay. So we are looking at these types of Riemann surfaces. Of course small x is a fixed point of capital X, alright, and of course I should also remind you that the upper half plane is biholomorphic to the unit disk, okay. So well, if you see, first of all, if X is simply connected, then pi 1 is 0, pi 1 of x comma x is trivial, is 0, okay, and x to x identity map is a covering, is the universal covering. So in this case X is biholomorphic to U, okay. So we look at the situation when the fundamental group is non-trivial, okay. So so first of all, so let me draw a diagram. So you have you have X here, and so I have the projection, the covering projection. This is X sub univ is U, okay. This is X sub unit, the universal covering space, and well, because of this if you fix a base point small x in capital X, then the fundamental group below is identified with a subgroup of holomorphic automorphisms above, and that subgroup is precisely the group of subgroup of deck transformations of this cover. Okay, so the corresponding diagram is well, let me also draw it here. So I'll have to write across this board. It's all right. So I have pi 1 of capital X comma small x. There is an identification. So I put this, say it's an isomorphism. This is an identification via P. That means because of this covering, and this identification is with the deck transformation group of this cover, which is a subgroup of the holomorphic automorphisms of the universal covering space. And well, I can go one step further and make you realize that this is sitting also in the holomorphic automorphisms of the whole complex plane. Okay, so if you want, well, it's maybe I remove this letter, these few letters, so that I have some more space to write. So let me remove this. So here is so this I write it as bi by holomorphic. Okay, and so this is sitting inside automorphisms, the holomorphic automorphisms of complex plane. Mind you that this is identified with PSL 2R. Okay, these are Moebius transformations with of the form z going to a z plus b by c z plus d with a b c d real numbers and ad minus bc equal to 1. Okay, these are the representatives here, and of course this is the full group of Moebius transformations, which is PSL 2C. So this is all complex entries. Okay, and this is a subgroup of that, right? So that is because of this covering. Now so I'm assuming that the first fundamental group is non-zero. Okay, assume the first fundamental group is non-zero. Well, so the first statement I want to make is that the deck transformation group can contain only parabolic or hyperbolic elements. Okay, this is what we have seen last time. I mean, elliptic elements are not allowed. Why they are not allowed is because an elliptic Moebius transformation will fix a point of view, and a deck transformation, a non-trivial deck transformation, is not supposed to fix any point. Okay, otherwise it will become equal to the identity transformation. So elliptic transformations are not allowed, and we have also seen that for the upper half plane the condition of loxodromic is the same as it being hyperbolic. A Moebius transformation which is loxodromic and which preserves the upper half plane has to be also hyperbolic, necessarily hyperbolic. Okay, so there are only two possibilities. So let me write that down here, because I want space for some more to extend this diagram. So there are deck U Px can have only parabolic and hyperbolic elements. Okay, so this is what we have from the last lecture, and you see I claim that because of this additional assumption that the fundamental group is abelian, which means that the deck transformation group is abelian. After all, the fundamental group is identified with the deck transformation group. I claim that because of this abelian nature, which makes every deck transformation commute with every other deck transformation. Okay, this commutativity forces two mutually exclusive cases, namely one in which all the elements are parabolic and the other in which all the elements are hyperbolic. so what I am trying to say is a parabolic and a hyperbolic element cannot commute, okay. So we will see why that is true. So so let me write a few lemmas. So let me write a lemma. Suppose A and A prime are Moebius transformations, with you know A prime is equal to A prime A, alright, that is A and A prime commute, okay. So and A and A prime are a pair of commuting Moebius transformations. Then A is a translation implies A prime is a translation, okay. So I'm just telling the very obvious fact that only translations can commute only with translations, okay. So what is the proof? The proof for this is, you see, you know, A is a translation means that A of infinity equal to infinity is the unique fixed point, okay. If A is a translation, then infinity is a fixed point, and you know translations are parabolic, okay. In fact an element is parabolic, Moebius transformation is parabolic if and only if it is conjugate to a translation. So and if it is parabolic, by definition it has only one fixed point, so infinity is a unique fixed point, alright. Now you see A prime A of infinity will be A prime infinity, okay. So what, but you see A of infinity is infinity, so this will tell you that A prime infinity has to be infinity. Why? Because you see, what does this tell you? A of infinity is infinity, so you get A prime infinity is A of A prime infinity, okay. That means A prime infinity is a fixed point for A, but the only fixed point for A is infinity, therefore A prime infinity is equal to infinity. But if A prime infinity is equal to infinity, then A prime is a translation, okay. So this implies, well, we have to say a little bit more. This implies that A prime of Z is of the form, well, it is of the form alpha Z plus beta. If infinity is a fixed point for a Moebius transformation, then it has to be of this form, alright, it has to be of this form. Now you see, put I mean I'm just trying to claim that this alpha is 1, I'm just trying to claim that alpha is 1, okay. So you put A as put A of Z, see after all A is a translation, so you write it as Z plus well, since it is A prime, let me put primes here and write for A of Z, Z plus beta, okay, and write out the condition that A prime A of Z is A prime of Z for every Z. So you know A prime A of Z is equal to A prime of Z for all Z. What this will tell you is going to tell you that well, so if I so what does it mean? First apply A, then apply A prime, that's going to be the same as first applying A prime and then applying A to Z. So first apply A to Z, I will get Z plus beta, and apply A prime to that, so I will get alpha prime Z plus beta prime is equal to, I will get here I have to first apply A prime, which is if I apply A prime to Z, I will get alpha prime Z plus beta prime, and then I have to apply A, which is just adding beta, okay. Now if you compare both sides, you will get that the beta primes are going to cancel, and then I will get, and then alpha prime Z's are going to cancel. I am going to get alpha prime beta is equal to alpha prime beta is equal to beta, okay. This is what I am going to get, and mind you of course I want to rule out the case that beta is 0, so that I can cancel by beta and conclude alpha prime is 1. So you see if beta equal to 0 corresponds to the case when A is identity, okay, and I am assuming let me assume that A is not the identity. I don't want to look at the identity transformation, okay, because that is not very interesting. A not equal to identity, okay, right. So A is not equal to identity, so beta is non-zero, therefore I can cancel beta and I will get alpha prime is 1. If alpha prime is 1, then A prime z is z plus beta prime, so it is also a translation, alright. So that proves this lemma, right. Now I will make another simple lemma. So what this tells you is that if a Moebius transformation commutes with a translation, then it has to be a translation, okay. Now but you know, translation is just up to conjugate, translation is just a parabolic element. So I am saying the same thing will happen for a parabolic element also, okay, namely if a Moebius transformation commutes with a parabolic element, it has to be parabolic, okay. So let me write that lemma. Suppose A and A prime commute, A is A being parabolic, okay. Suppose A and A prime commute, A being parabolic, okay, then you know A prime is also parabolic, then A prime is also parabolic, right. So what is the proof? The proof is, well, you see A is parabolic, so by our characterization of parabolic transformations you can find a B such that conjugating A by B makes it a translation, okay. So can find B such that B A B is B inverse is a translation, okay. And well again in all these cases, you know, the case when one of the transformations is the identity transformation, I am not at all worried about that case because that is the uninteresting case, okay. So well BA B inverse is a translation, but now notice, so that means what, BA B inverse has unique fixed point infinity, it means a translation. Now you see B A prime B inverse times B A B inverse, okay, this will be just B A prime A B inverse, but this is B A prime B inverse because A prime A is A prime, and then I can write it as B A B inverse B A prime B inverse. In other words, I am just saying that because A and A prime commute, so do their conjugates by B, okay. Now look at lemma 1. Lemma 1 says that if two Moebius transformations commute and one is a translation, then so is the other, okay. So by the preceding lemma, by the previous lemma, what will happen is that B A B inverse is a translation, so B A prime B inverse is also a translation, and you see if B A prime B inverse is a translation, then of course A prime is parabolic, okay. So the moral of the story is that if the deck transformation has one parabolic element, then every element is parabolic, I mean, so it contains only parabolic elements, okay. So if so either deck U Px has only parabolic elements or only hyperbolic elements, So the moral of the story is that you have two distinct cases, mutually exclusive cases, one in which the Deck transformation consists of only parabolic elements, the other one is the case when the Deck transformation consists only of hyperbolic elements. Okay, so let us assume that the Deck transformation group consists of only parabolic elements. Okay, assume the former, namely the Deck transformation group has only parabolic elements. Okay, so so here again I will distinguish between two cases, just for clarity. Suppose one of the elements of the Deck transformation group is a translation. See, after all, the Deck transformation group contains parabolic elements. Okay, and if necessary I can make a conjugation and make a parabolic element into a translation, but even without the necessity of that, suppose there is one element, namely a parabolic Deck transformation, which is already a translation, then you see again this lemma will tell you that all other elements are translations. Okay, then by the first lemma above all elements are translations. All the elements are translations. Okay, now you see, so what happens in this case is, well, you see you have Deck transformation group is, well, it is identified with a subgroup of translations. So translations are of the form z going to z plus beta. Okay, this is a group under addition translations. Okay, I mean if you well, I mean this is a group under composition of mappings, and if I identify z going to z plus beta with say the complex number beta, okay, then this is identified with complex numbers, and this is well, this is a group under addition. So the translations are Moebius transformations under composition, and identifying z going to z plus beta with beta, the complex number beta, will identify this abelian group of translations under composition with the additive group of complex numbers. Okay, now notice that so I again want to make the same statements that I did when we were trying to classify Riemann surfaces with universal covering space, the complex plane, and with the non-zero fundamental group. Okay, if you go back and recall what happened at that time, we found that the fundamental group turned out to be certainly abelian. That was because just like in this case, we were able to identify the Deck transformation group as a subgroup of as a subgroup of an abelian group, C under addition, okay, and subgroup of translations. Okay, and then there we made the statement that the Deck transformation group is a discrete Z module. Okay, and the discreteness came because of the fact that this is a universal covering and these are Deck transformations. Okay, and then we gave the statement that a discrete Z submodule of C has to be either generated by one integer multiples of one non-zero complex number, in which case it is isomorphic to Z, or it is generated by integral multiples integer linear combinations of two non-zero complex numbers with non-real ratio, in which case it is isomorphic z cross z. Okay, so in the by the same kind of argument, what you can see is that the deck transformation group is a discrete z submodule of C. Okay, so this the argument the proof of this is exactly as it was for the case when the universal covering was the complex plane. Alright, there is no difference in the proof, but there is something new now. You see, notice that these are all holomorphic automorphisms of U. Since these are holomorphic automorphisms of U, I want you to remember that the entries beta that you get here, that is the image of this there, okay, is going to land inside R. Okay, the elements here are certain holomorphic automorphisms, the upper half plane, but the holomorphic automorphisms, the upper half plane, are Moebius transformations with with of the form z going to az plus b by cz plus d with a b c d real. Okay, so the point I want to make is that beta is real. Okay, so so what you actually get is a discrete z submodule of C which is contained in R, okay, which is contained in R. Okay, so so now we have this now let me recall that lemma. A discrete z submodule of C can have only three possibilities: either it is 0 submodule, or it is isomorphic to Z and it is integral multiples of a single non-zero complex number, and the third case is it is isomorphic to Z cross Z and it is integer linear combinations of two non-zero complex numbers, but these two non-zero complex numbers are supposed to have non-real ratio, that means they are supposed to be linearly independent over R. But you see, if it is contained in R, I cannot find two entries which are linearly independent over R itself, so therefore the only possibility is that it has to be isomorphic to Z. Okay, so therefore the deck transformation group is isomorphic to Z. Okay, the deck transformation group is Z, there is no other choice. Okay, and the isomorphism is given by so that means there is a generator here, okay, and the generator is a translation, okay, and every other translation is just applying these translation or its inverse finitely many times. That is all that you have in this group. Okay, so the amazing thing is that in this case the deck transformation group is just isomorphic to Z. Okay, fine. So so I've taken, so this is the case when one of the elements is a translation. Alright, now suppose one of the elements is not a translation. Okay, let me go to the other case. Then of course all the other elements are also not going to be translations, because the translations commute only with translations. Alright, so suppose on the other hand that one of the elements of deck is not a translation. Suppose it is not a translation, alright, then every other member is also not a translation, because they all commute with this one, okay, because it is a commutative group. Then the same holds for So let me call that element as A. Suppose one of the elements A in the deck transformation group is not a translation, then the same holds for all other elements, namely all the others are also not translations. Okay, again you can find a B so that BA B inverse becomes a translation. After all, B is going to be the a Moebius transformation that is going to take the fixed point of A to infinity, that is all you need, alright. So choose a B so that BA B inverse is a translation. Okay, I can choose a B so that BA B inverse is a translation, but you know if BA B inverse is a translation, then BA prime B inverse is also a translation for every other element. That is because all the BA prime B inverses, they will all commute with BA B inverse. Okay, so then as seen in this second lemma above, as seen in the second lemma above, B A prime B inverse is also a translation for every A prime in the deck transformation group. Okay, so what is the situation now? The situation now is that again you will find that the deck transformation group is isomorphic to Z. Okay, only thing is that you have to shift to an isomorphic cover. So how do you do that? Let me go back to this diagram here, and write it down. So you see I have this B, you see what is this B? So I have U sitting inside the complex plane, okay, the upper half plane sitting inside the complex plane. So this is a subset relationship that I have written. Don't confuse this with U, I am just writing U subset of C, alright. And then I have this B, you see B is a Moebius transformation, alright, and B will take C to C. Okay, in fact if you want maybe I should put C union infinity because it may take a finite point to infinity, so I have to take the whole so here again I think I have made a mistake, in fact I should write C union infinity. Okay, this is of course the whole group of Moebius transformations including the point at infinity. Okay, if you take only holomorphic automorphisms of C, then it is always of the form, it is upper triangular form. Okay, so you won't get PSL to C. Okay, so please correct this small mistake. Okay, so well I have U and this is B of U. So B of U, well U is in this upper half plane in C union infinity, and B is an isomorphism of C union infinity, and it will take U isomorphically to B of U. Okay, and if I take this map defined to be defined by the commutativity of this diagram, it's first apply B inverse then apply P, then you see this is also a covering. After all it's an isomorphism followed by a covering, so this also a covering of X, this also universal, and this also universal covering because after all BU is isomorphic to U, it's biholomorphic to U, so it's also topologically homeomorphic to U, so it's also simply connected. So this is also another avatar of the universal covering for X. Okay, now what happens to this when I do it at the level of deck transformations? So what's going to happen is just like this covering identified the fundamental group here with the the deck transformation group as a subgroup of holomorphic automorphisms above, the same thing should happen here. So what I am going to get is I am going to get something like this. So I will get another isomorphism identification, this is via P circle beta inverse, P circle B inverse, okay, and this is going to give me the deck transformation group of the other isomorphic cover, namely B of U P circle B inverse X, okay, and this is going to be, well this is a subgroup of the holomorphic automorphisms of B of u. B of u is some domain in the complex plane which is biholomorphic to u, right, and of course this is again contained inside the well automorphism group of all Moebius, I mean all possible Moebius transformations, right. And what is this map? What is this map? This map is just, so how do you get a deck transformation here? Okay, well I take a point here, I go by B inverse, apply a deck transformation there, and then come back. This is how, starting with a deck transformation here, I produce a deck transformation there. So what is the map here? The map here is just conjugation by B. It is just A going to B A B inverse. Okay, so give me a deck transformation A here. Okay, give me a deck transformation A here. That is by definition a holomorphic automorphism of U, which is going to preserve the fibers. Okay, and how do I, to what deck transformation does it go here? It's just its conjugate. Okay, so this is just A going to B A B inverse, and it's the same map everywhere. So there is an isomorphism like this, there is an isomorphism like this, there is an isomorphism like this. In all these cases the map is just A going to B A B inverse, right, that is the map. It is just A going to B A B inverse, alright. So so here also it is a map A going to B A B inverse. Okay, so this is the map I am looking at. So let us go back to the current situation we are in. We have taken the situation that all the deck transformations are not translations, but then we conjugate by a single, we pick any one deck transformation and you conjugate it with a single B, so that after conjugation it becomes a translation, then everything becomes a translation, alright. So what happens is that this, so what is this? This is, see, this is just B dot deck U P x dot B inverse, that is what it is. It is, you are actually conjugating the whole group by B, okay, and well let me draw a line so that it does not, okay, and so in this case this group, namely this, now this is a subgroup of translations, okay, this becomes a subgroup of translations, alright, and again it is going to be a discrete, it can be identified with the discrete Z submodule of C contained in R, okay, it is going to be the same thing as the earlier case, and that will force that this is isomorphic to Z, okay. So in both cases the deck transformation group is actually isomorphic to Z, the integers, and it is generated by a single translation, okay, namely it consists of integer multiples of a single translation, or rather I should say translations by integer multiples of a single non-zero complex number, okay. So in this case deck U P x is isomorphic to deck B of U P circle B inverse x, which is equal to, incidentally, the conjugate of this, it is just B dot deck U P x dot B inverse, and this is isomorphic to Z, okay, because again let me repeat, it is discrete, it is a discrete Z submodule of C, and it is going to land inside R, okay, it is a discrete sub. So as linearly independent elements over R, it can contain only one, okay, in which case you can get only Z, okay. The only other possibility is you can get Z direct sum Z, you cannot get Z direct sum Z, okay. because you cannot find two translations here, you cannot find two real numbers which are linearly independent over R, okay. R over R has dimension 1, okay. Any maximal linearly independent subset has only one element, right. So the moral of the story is that if your deck transformation group consists of only parabolic transformations, in that case the deck transformation group is just isomorphic to Z, okay. Now I am going to say that literally the same thing happens in the other case, namely when the deck transformation group contains only hyperbolic elements, okay. So let me do that. I think I will retain this diagram on this side, right, and I will kind of so what I am going to do is let me draw a line so that, okay. So let us go to the other case. Assume the deck transformation group U Px has only hyperbolic elements. Assume it has only hyperbolic elements, okay. Now so again, you know, a Moebius transformation, so let us pick one, hyperbolic element, and you know, if you take a hyperbolic Moebius transformation, then you can conjugate it by a suitable Moebius transformation so that its fixed points are of the form are 0 and infinity, so it is of the form z going to lambda z, and if this Moebius transformation is going to preserve the upper half plane, then you know lambda has to be real and lambda has to be positive, because I mean that is a characterization of hyperbolic Moebius transformations, okay. So pick a not equal to identity in the deck transformation group and find B so that B inverse of Z is lambda Z, lambda is going to be real, lambda is positive, okay. So this is possible because of our characterization of hyperbolic Moebius transformations, right. Now I want to say that if you take any A prime, because every other A prime here commutes with A, I want to say that if you conjugate every other A prime with the same B, it is still going to be of the same form, that is what I want to say, okay. So suppose A prime is another deck transformation, okay. So mind you, if A already has fixed points 0 and infinity, if A already has fixed points 0 and infinity, then you can take B to be identity, okay. You do not have to really look for a B different from the identity, right. So suppose A prime is a deck transformation, is another deck transformation in this group, then again you see B A B inverse and B A prime B inverse commute, okay. We have seen that this is true because A and A prime commute, alright, and if you look at B A B inverse of B A prime B inverse of 0 is equal to let me put Z I am just writing the commutativity out, okay, and what I am going to do is I am going to put Z equal to 0, you put Z equal to 0, what I will get is I will get BA B inverse of BA prime B inverse of 0 is equal to BA prime B inverse of 0, because BA B inverse of 0 is 0, okay, alright. So what it will tell you, and if I put if you put z equal to infinity, okay, you will get BA B inverse of BA prime B inverse of infinity is equal to BA prime B inverse of infinity. So what this will tell you, if you put 0 z equal to 0 and z equal to infinity, it will tell you that BA prime B inverse of 0 and infinity are the two fixed points of BA B inverse, so they are one among the 2 points 0 and infinity. So this will tell you that BA prime B inverse of 0, BA prime B inverse of infinity, they both belong to 0 infinity, they have to be one of these two, okay. Notice that these two are going to be fixed points for BA B inverse, and BA B inverse has precisely two fixed points. A Moebius transformation cannot have more than two fixed points. Those two fixed points are 0 and infinity because of this form that we have assumed, right. So now we claim the obvious that BA B inverse, BA prime B inverse of 0 is actually 0, and BA prime B inverse of infinity is actually infinity and not the other way around. That is where we use the fact that A prime is actually hyperbolic, okay. So the claim is B A prime B inverse of 0 equal to 0, B A prime B inverse of infinity is equal to infinity, okay. This is the claim, right. Well, of course they can't be equal, because Moebius transformations are one to one, they cannot be equal. So either this is equal to 0 and that is equal to infinity, or the other way around, this may be infinity and that may be 0. If you assume that, you will get a contradiction. So we can try to work that out. Suppose not. So B A prime B inverse of 0 is infinity, and B A prime B inverse of infinity is 0, okay. Well, you see, I will work out a small lemma. This must be obvious to you, but we can write it out. If A double prime of 0 is infinity and A double prime of infinity is 0, then A is elliptic, okay, because you see proof is, you see, write A double prime of z as A z plus B by C z plus D, okay, with AD minus BC is equal to 1, write it in this form, okay. Now A double prime of 0 is infinity, okay, so when I plug 0 inside this I should get infinity, that means the denominator should vanish, okay, and so when I plug in 0 I get infinity. So let me write that down. I will get B by C z plus D is infinity, okay, and this should force that C is 0, no, I will get B by D, so I will get B by D, sorry, I will get B by D, and this will force that D is 0, alright. I cannot divide a complex number by another to get infinity unless the denominator is 0, okay, and if D is 0, mind you, so that will tell you already that BC is minus 1, okay, and then A double prime of infinity is 0, okay, so when I plug in infinity, if it is 0, see the point is you divide both numerator and denominator by z, so you can also write as, if so long as z is not 0, you can write as A plus B by z divided by C plus D by z. If I plug in infinity, the 1 by z terms will go off, so I will get A by C, so I will get A by C equal to infinity, I mean A by C equal to 0, that will tell me that A is 0, okay. So therefore what I will get is, I will get A double prime matrix as matrix is of the form, well, A is 0, B is as it is, C is minus 1 by B, okay, and D is 0, okay, and you see this is of course determinant 1, alright, but what is its trace squared? Trace squared is 0, that means it is elliptic, okay. Trace squared A is 0, that implies A is elliptic, okay. So that proves this lemma. So now if you look at this lemma, then B A prime B inverse of 0 is infinity and B A prime B inverse infinity is 0. If that happens, then B A prime B inverse will become elliptic, that means A prime is elliptic, but we have assumed A prime to be hyperbolic after all, so it is not possible, okay. So so the claim it holds, okay. So the moral of the story is that this claim holds, and therefore if you take any other deck transformation A prime, then B A prime B inverse is also of the form z going to some mu of z, alright, where mu is, and it's hyperbolic, so that mu is real and mu is positive, okay. So this implies B A prime B inverse of z is equal to some mu of z, mu real, mu positive, okay. And of course please remember that in all these cases lambda is not 1 unless A is the identity, unless A is the identity lambda is not 1. So if I have taken A not equal to identity, then this lambda cannot be 1, and if A prime is not identity, then mu cannot be 1, alright. Now mind you, again I have the same kind of situation. So you see again what will happen is that I will have deck transformation group of the original cover U P X isomorphic to the conjugate, which is the deck transformation group of this isomorphic cover P circle B inverse, okay, which is just a conjugate of this by B. So it is B dot deck U P X B dot B inverse, this is a conjugate, okay. And well, you see what this is a subgroup of Moebius transformations of the form z going to mu z, mu real, mu positive, okay, okay. It is a subgroup of that, alright. And you see notice that the composition here will be corresponding to composition here, but then it will become multiplicative, okay. If I compose z going to mu1 z with z going to mu2 z, I will get z going to mu1 into mu2 z, okay. So you know, if I want to identify it with additive submodule of C, I have to take a log, okay, and the log will convert this multiplicative group into an additive group, alright, and I can take log because mu's are all real positive, alright. So what I do is I simply take the log map, okay, I take the log map, namely I just send z going to mu z to just log mu, okay. So this is the real logarithm, this is the real logarithm to the base e, right. So I take this, and what I end up with is well, this is identified with this is a so what I get is going to be this is going to be identified with r plus under addition, r plus under addition. So r plus is why do I get oh yeah, I need also negative variance, so I get r under addition, right. So correct, I can have negative logarithms if mu is less than 1, correct. So this identified as a additive subgroup of R. So under this identification the deck transformation group becomes an additive subgroup of R, okay. Again it will become a discrete Z module, it will again become a discrete Z submodule of C, the additive subgroup of C, which is contained inside R. Okay, so again the same argument as before applies, and it will tell you that it is isomorphic to Z. Okay, so mind you, this is contained in C comma plus. After all, R comma plus is a Z submodule of C comma plus, right? So again dec U P X is identified with a discrete Z submodule of C contained in R. Okay, the discreteness can again be proved in a similar way, okay, by making use of these admissible neighborhoods. Okay, so you again prove the discreteness, alright, and it becomes a discrete Z model of C contained in R, and therefore it is isomorphic to Z. Okay, hence isomorphic to Z. Okay, so the moral of the story is, if you have a Riemann surface X with fundamental group abelian, that is very important, and universal cover the upper half plane, then its fundamental group is just isomorphic to Z, you do not have any choice, alright. So that is the upshot of the whole argument. Okay, so hence any Riemann surface with abelian pi 1 and universal covering U has pi 1 isomorphic to Z or pi 1 isomorphic to 0, okay, or pi 1 equal to 0. Okay, now well, actually this argument gives you also the coverings of I mean also the classification of Riemann surfaces which have upper half plane as universal cover. Okay, we just have to go a little bit more and write it down, but what is more striking is that one can write down the following theorem. So theorem, if X is a Riemann surface such that pi 1 of X is isomorphic to Z cross Z, then X has to be a complex torus. So here is an amazing theorem. You take a Riemann surface with fundamental group isomorphic to Z cross Z, then it has to be only a complex torus. Okay, and what is the proof? Well, the fundamental group is not 0, so the universal cover cannot be P1, cannot be the external complex plane C union infinity, which is P1, because in that case the fundamental group is 0, right. If of course the universal covering is the complex plane, we have already proved that if the fundamental group is isomorphic to Z cross Z, okay, then it is a complex torus, alright, and the covering space cannot be U, the universal covering cannot be U, because we have just now proved that if the universal covering is U, then the fundamental group is isomorphic to Z, and Z is not isomorphic to Z cross Z, alright. Therefore you see it is an amazing theorem that you put a topological condition on the definition of Riemann surface, and the theorem tells you that it has to be of a particular type. Okay, so you get that as an upshot of this, right. Okay, so let me make a few more remarks to complete this discussion, right. So let us look at both of these cases when the universal covering is the upper half plane, and either the Drake transformation group contains only parabolic elements or only hyperbolic elements, and look at what the coverings are. Okay, so let me write that down. If X has universal covering U, okay, and deck and the deck transformation group. So I should say and fundamental Abelian and Abelian fundamental group. We have two cases. So case 1, the deck transformation group is isomorphic to Z, okay, and is generated by a translation, let me say by a parabolic element, okay. We have this case, okay. We may choose so let me take the generator as A, okay. Choose B so that you see B inverse of Z is Z plus 1, okay. So in both cases you are conjugating the whole deck transformation group by a single Moebius transformation that makes it into completely a group of translations in the parabolic case, and in the other case of course it becomes a multiplicative group of transformations of the form Z going to mu Z, right. So we are in the first case, right. So you can without loss of generality choose the B so that the translation that it is transformed to is Z going to Z plus 1, alright. Now see what will happen is, so you see I have this diagram, so I have B of u to x, okay. I have this covering P circle B inverse, okay, and this is also the same as taking B of u and well going modulo this translation group, okay. So this is going modulo Z, okay. So you see Z is just identified with the conjugate of the deck transformation group by B, which is actually the deck transformation group of this cover, alright. And you see this this covering map in this case can be identified, it can be identified with so this is something that is isomorphic to U, alright. So it can be identified with U to U mod Z, okay. It can be identified in this way, alright. So let me put it like this, you can find an identification like this, and this map is just the exponential map Z going to e power 2 pi I Z, okay. So what you must understand is that we have already seen that the exponential map is a covering map from C to C star, okay. The exponential map is a covering map from C to C star, alright. And but if you instead of C star, if you take delta star, which is the punctured unit disk, the unit disk minus the origin, and you take the inverse image, okay, it is a restriction of a covering map to an open subset of the base, so that continues to be a covering map. So this is still a covering map, and the fact is that this is delta star, this is delta star. Delta star is just the punctured unit disk, it is the unit disk minus the origin, okay. So the moral of the story, so you can check this, the moral of the story is that in the parabolic case the covering, mind you we already know that these two can be identified, okay. If you give me a universal covering, then the covering space modulo the deck transformation group can be identified with the base, alright, and I am saying that this can be identified as a covering with U to delta star, the exponential map. Okay, therefore the moral of the story is that in the parabolic case your Riemann surface is actually biholomorphic to delta star, okay, and the covering map can be identified after choosing isomorphisms. You can identify it with the exponential map restricted to delta star, okay. So you get this is the parabolic case, right, okay. Then let us go to, so let me put this the other case is the hyperbolic case, that is when the deck transformation group consists of only hyperbolic elements. So in that case again one can do the following computation. Case 2, the deck transformation group is of course isomorphic to Z again, and is generated by a hyperbolic element A, okay. In this case of course you can choose B inverse, so that the element so that B inverse, you can choose B so that B inverse is a form Z going to lambda Z, lambda real, lambda positive, okay. And in fact I can make sure that the lambda that I get is less than 1, because I have to only use an inversion, okay. And if I modify it by an inversion, if I conjugate by an inversion, okay, I can make sure the lambda is less than 1. So let me write that down. Choose B so that B inverse of Z is lambda Z, lambda positive, lambda real, of course lambda real, lambda positive, lambda so I need I can make lambda less than 1 or greater than 1. So let me see what I want lambda greater than 1, okay. So we can do this, okay. If lambda is less than 1, all you have to do is just use an inversion, okay. You have to conjugate further by an inversion, then that will amount to replacing lambda by 1 by lambda, which will be greater than 1 if lambda is less than 1, okay. So you can do this, okay. Then so in this case what happens is that you see B of u, so if you have this covering P circle B inverse to X, and this is of course identified with B of u mod Z. Now this Z being identified with this Z here being identified with the conjugate of the deck transformation group as before, so I will not write it down, but I want to say is that what I want to say is that I can identify this with again with u, and I can identify this with delta sub r, okay. So this is something that I want you to check, okay. So this delta sub r is the set of all Z in C such that r is less than mod Z less than 1, okay. So it is an open annulus with outer radius 1, inner radius r is a fraction, r is a number between 0 and 1, alright. And how is r given? R is given by a formula, so let me write down that formula. It is e power minus 2 pi squared, it is e power minus of 2 pi squared by log lambda, okay, alright. Here of course this is the natural logarithm, alright. This is the value of r, okay, and this map from u to delta r is none other than the map Z going to, it is also an exponential map, it is just Z going to e power 2 pi I log Z by log lambda, okay. I want you to check that this is a covering map, I want you to first check that this is the covering map, alright, which is quite easy to do if you know the properties of the exponential mapping. And mind you, the logarithm that I am using here is the principal branch of the logarithm, okay. When you say logarithm of a complex number, it is a multi-valued function, so you have to choose a branch, and I am choosing the principal branch of the logarithm here. And of course this log lambda is of course a real logarithm, there is no problem with that, okay, and you can check that this is the covering map. So the upshot of the story is that if you have a Riemann surface with universal covering U, either it is U itself, which is the same as delta, okay, or if it is this case it is delta star, okay, or if it is this case it is delta r, delta sub r, okay, for r a fraction running in 0 1, okay, and in fact it's further also true that if I change r, then these delta r's are not biholomorphic to one another, okay, so that's something that you can check as an exercise, okay, by using universal properties, by using the properties of universal covers you can check that, okay. So all these delta r's are distinct for distinct r's, okay, so this gives you all possible cases for Riemann surfaces with abelian pi 1 and universal covering U, okay. So what I want to say at this stage is that we have kind of completed the first classification of all, which includes all Riemann surfaces which have abelian fundamental groups. So we have classified all Riemann surfaces with abelian fundamental groups, okay, and we have also so what is left out is Riemann surfaces with non-abelian fundamental groups, okay, and the compact Riemann surfaces of genus greater than 1, okay, that is those complex structures, Riemann surface structures that you can put on a G torus, okay, G greater than 1. So these are G tori which have been stuck together, okay, and you get a G torus, and if G is greater than 1 then the universal cover has to be U, okay, the fundamental group is not abelian, okay, because if the fundamental group is abelian we know all the cases. The fundamental group is non-abelian, you can see it otherwise also, the universal covering has to be U. So if you are interested in compact Riemann surfaces of higher genus G greater than 1, okay, then you will have to study the Moebius transformations on the upper half plane, okay, that is the clue to studying compact Riemann surfaces of genus G greater than 1, that is what this study says, okay. So I will end with that.